And what we'll do is we'll go over here. And you are on. Let me give you a little intro. Okay. So thank you for coming to the presentation. Jeff, we're going to start. Hello, Jeff. I'd like to welcome Justin from Sikorsky. He was very interested in doing open water search and rescue project with an unmanned mission vehicle based on multiple drones in a mesh network. And so without further ado, I'd like to present Justin, who will now describe his master's thesis.
Thank you. Good afternoon. Graduate student here at Fairfield University, pursuing master's in computer and electrical engineering. Today, as was said, I'm going to be presenting my master's thesis for a system for open water person detection. This system is going to take advantage of sensor fusion using multiple infrared sensors connected on multiple drones through a mesh network in order to search for people in open scenarios such as on the ocean. This presentation is broken down into 4 sections. In the introduction, we're going to review the problem statement, the current market for search and rescue, and what the contribution of this thesis will be. In system design, just going to go over the basics of each of the devices that are in the system and the choices we made for the components that make up these devices. To evaluate our system design, we did experimental testing. I did experimental testing, which we will discuss the setup and the parameters and the results of that experiment. Finally, bringing it all together, we're going to note some observations made for specifically the FLIR infrared camera that we utilized for this project, the results, draw conclusions, and give perspectives on future improvements that can be made and other works in this area. First, introduction. Problem statement. In order to locate a person requiring rescue, we seek to design and implement a system that makes use of a mesh network with multiple unmanned aerial vehicles equipped with imaging sensors in order to locate a person. Currently, the search and rescue missions are performed by manned, expensive vehicles such as the S-92 shown here. Helicopters are very prevalent in search and rescue. However, we are looking to develop a system to replace or augment this search and rescue vehicles using multiple inexpensive drones in comparison to the expensive cost of a helicopter. Typically, these are funded by government agencies, but in some cases, such as the Bristow Group shown on the slide, which is a private organization that contracts the UK, and we took a little bit into the cost of their operations. From the World Factbook, there are approximately 74 countries that have the resources in order to service and maintain helicopters, and also have a significant coastline that would institute possibility for search and rescue. Given the S-92 numbers of a $27 million aircraft and a $900,000 a year upkeep, this would come out to approximately $2 billion in assets and $66.6 million per year in upkeep, assuming each of these 74 countries has at least one aircraft for search and rescue. My contribution is trying to take advantage of low costs and low complexity of commercially available sensors on the market today. develop an image processing of this data from the infrared sensors and communicate results over a mesh network in order to locate people at a reduced cost to current methods. System design. The system will consist of multiple drones. Shown in the above architecture, there are two with an optional ground station. The ground station in each of these drones will be nodes in a mesh network. Drones will perform search of an open area, such as an ocean, for people using infrared sensors. Any person detected or possible person detected in the scene will be communicated with the rest of the network and the image stored locally. The ground station, which is optional, can connect to an individual drone. For our prototype, it was connected over a local area network as opposed to the mesh network. And through this access, can take off any images stored by the unit or the logs of other information that the drone collected. In addition, it gives it access to interfaces from the software that was developed, and also some available software for live video feeds from the infrared cameras. Mesh network. For my system, I selected to use a mesh network. A mesh network is a type of network topology which consists of many nodes. These nodes connect to as many other nodes in range as possible to pass along data to create this network. Why did we select this? Mesh networks have a lot of pros over conventional networks, as there's no hierarchy, so you're not required to have a main hub. Additionally, they are adaptable, which is a special advantage in areas that we may be flying these drones in inclement weather, in which reception may not be the best. So the network is still maintained when you may have intermittent connections between nodes. Each of the devices in the system will be equipped with one of these network adapters. For the actual component selection, we went with a XB Zigbee adapter from DigiKey. They offered a kit. The XB Pro offers a 2-mile range with line of sight. An additional reason that this kit was selected was its very simple implement into the Raspberry Pi. The software was very straightforward and just needed to use the available serial library from the Raspberry Pi. These are the two examples of our send and receive routines that were used. The first and primary device of this system is the image capturing device. For full implementation, multiple of these devices will be used, and it's expected that the system be scalable to use many more of these devices to cover a larger area. The above diagram, or the shown diagram, is of this device. Each of these devices will be run on a Raspberry Pi. A maker-focused Raspberry Pi battery pack will be utilized as the power source. Each of them will contain an infrared camera, onboard storage, utilizing the existing storage available to the Raspberry Pi, and will also contain the XB adapter. The battery pack was just a run-of-the-mill battery pack. Third-party benchmarking shows that it should have a power capacity for 3.8 hours, given a decent amount of computing power. For a typical process, images from the IR camera will be captured and processed at regular intervals. For our software, we chose 1 frame a second to not overburden the system, but also still give reasonable returns. If an object is detected after processing, it'll be stored on board, and in the image file will be stored on board, and in turn the device's serial number and image name will be transmitted over the network for the rest of the nodes in the network to log. This gives it the availability that any one drone should have a full list of all potential objects detected by the system, and in the event that a drone detected an object but was lost subsequently, that area can be rescanned, or if no objects were detected, they can know that that area was void. Before I settled down on a specific camera, I looked at many infrared cameras, learned a bit about the range. So the infrared spectrum is actually a fairly large spectrum. It goes from the very edge of visible light out to microwave frequencies. However, all these frequencies are not related to heat. Only very specific frequencies are. For example, just looking at these cameras shown on the chart, you would expect that for image processing you would want to select a higher resolution camera, especially when you're looking at objects at range. However, this one is actually a fairly cheap night vision camera, as it's advertised, but the frequencies that it deals in infrared are actually just above red light, and it actually behaves very similarly to visual light, and warm bodies do not emit this radiation, but rather it requires illumination. So these typical night vision cameras will actually have a flashlight on them that shines infrared on the scene to illuminate targets. However, in search and rescue operations, if you're going to be shining a light, you might as well just shine a standard visible spectrum light and use visual spectrum cameras. Additionally, a high-powered illumination in the infrared spectrum could cause damage to people's eyes, as they react differently than they would to a high-power visual light. The FLIR Star Sapphire 3 is actually a typical FLIR sensor that is used on helicopters such as the S-92. You can see by the price, they can go up quite a lot, whereas the resolution that they offer isn't that high of resolution. A lot of the cost actually has to do with special lenses that they have in optics. Whereas our cameras doesn't have any zoom features. Their cameras offer optical zooms up to 71x. Eventually, after some testing, we decided to go with the FLIR Lepton. An example of some basic testing that we did is producing the image that's on the right of the screen, which was taken with the FLIR Lepton of a person at 30 feet. It was taken in full darkness with no illumination. The exact same image was taken with the Hayworld camera, and it returned completely blank because the illumination source wasn't powerful enough to reach and illuminate the target, even though it had high resolution. These are some images of the camera that we chose. FLIR Lepton, long-wave infrared camera, but it only has a resolution of 80 by 60. However, each individual pixel is it's able to detect heat sources very well compared to a higher resolution camera that is not in the spectrum. From this, we go to the software that we use. So the 80 by 60 is just an array of pixels with values from 0 to 255. From these arrays that are captured, we compile a baseline image to, it's expected, especially in scenes such as oceans, to be somewhat uniform across the entire scene. So really you're looking for anomalies outside of this scene. So we construct this scene, which is it's a rolling average of 90% of the existing scene and then adding 10% of the newly captured image. Before the new baseline scene is calculated, we compare the recently captured image with that baseline, as seen here with an example results. These pixels are then looking for a delta of 20 value over the baseline scene, which equates to approximately 11.7 degrees Celsius. And then the largest of those deltas is used for the center of the image when it comes to drawing boxes, which we'll see later around the object. Issues observed with infrared. So while performing some of these tests, I observed some characteristics of infrared which impacted how I was developing this system. Images shown here are taken with the FLIR 1 product, which uses the same family of chip as our system was used. However, it had slightly higher resolution due to a newer chip becoming available since the purchase of our chips and design. As seen here, both glass and water block the infrared, glass more so than the water, but in both cases it completely blocks the heat of my hand in the picture. Even when the hand is removed, the dampness will reduce the infrared signature. So when we were looking at our non-ocean results, we looked at them knowing that the objects would most likely become smaller as the objects in our scene are typically around a 6-foot person, whereas the objects you'll see in the water, unless they're in some sort of life raft, will most likely be mostly submerged with only their head visible, and that head and hair may also be damp, so that would further reduce the signal. For our device, developed a 3D printed enclosure for the prototype, shown here. I also have an example that we can take a look at afterwards. Used to encapsulate all the devices. This would definitely be an area for improvement in the future. Since the prototype's been proven out, if we were to go on further, there's many redundant components in here, such as the XB mesh network adapter being redundant with the onboard Raspberry Pi chip, along with many ports that are unused on the Raspberry Pi. Example of the internals. For space savings, we needed to access the USB ports, and to save space we had quite a few 90-degree adapters and 90-degree cables to it. As I said before, we had a lot of cons with the prototype being redundant components and inefficient use of space. However, printed circuit board could fix that. Thermal test. There was a lack of data when it came to the components we selected, as well as the thermal properties of the 3D printed device, and I did not have a a thermal mitigation plan for this box. So to determine if I needed to create one, performed a simple thermal test. Test lasted for 55 minutes on battery power. 24 of these minutes was just the operating system running, and then for the remainder 30 minutes, the image processing was turned on in an environment that it did detect some objects. It was performed at night, and it was approximately 21 C or 70 degrees Fahrenheit. At this time, 2,000 images were captured, processed, and stored. And as I drew my conclusions from this chart, that no additional thermal plan was needed as the temperature was stable throughout the entire test. The spike that you see at the 24 minutes is the switching on of the image processing and more computing power. All these temperatures were taken from the onboard temperature sensor on the Raspberry Pi CPU temp. The ground station. This is used to access the Raspberry Pi of the image capturing device when there are no peripherals attached to the Raspberry Pi. The enclosure does not have any access to the HDMI ports or the USB ports from outside the box. So to avoid having to completely remove the Raspberry Pi to access anything on it, we used VNC Viewer, which can be run on any Windows computer. I'm sure it can run on others as well, but ground station that I had was a Windows PC, and they must be on the same local area network. VNC Viewer is shown on the bottom, and on the right is an example of some of the UIs that were used or created for the software. So the top image in that UI is the calculated baseline scene, and the bottom is the last image that it detected an object. And this object is a lamp, which happens to be warm. And that's off a bit, but still legible. So the breakdown of the cost. On the left-hand side, we have a full breakdown of a single image capturing device parts list, which comes out to $603.52. Theoretically, a device that costs this much, we could have a system replacement with 35 of these devices that would cost less than the monthly upkeep of one S92. So 35 of these devices would cost approximately $74,000, including a ground station. On to testing. So the goal of our testing was to determine success rate, or when there's an object in the scene that the device was able to detect it at some point before the object left the scene. In addition, what the system's response time is for those objects that it does test or detect, or rather how many frames the object is in the scene before it is detected. To accomplish this, we stored all the images and reviewed them post-test. And the scene had a sparse distribution of people so that it didn't overload and try to detect multiple objects at the same time. And there were instances, and then all these instances of object detection should be monitored closely for a pass-fail. And we'll review the images before and after a object is first detected to determine how many frames that object was in the scene before it was detected. For the scene setup, the device was placed in a third-story window of an apartment complex with view of the courtyard, which is approximately 60 feet below the window, and the street, which is approximately 115 feet away. The image on the right is an example of what the image capturing device was viewing at the time of the test. The test lasted for 30 minutes and 118 images were captured and processed. 5 controlled events were taken of people walking into the scene. These were purposely done at certain timestamps to allow us to control which images and to know that there were, during this 30-minute process, at least some people in the scene. For the results, 100% of the controlled events, or all the events that we detected people, were detected by the device. 4 of these scenes, the first available frame, the device did detect that there was an object in the scene. 1 of these detections happened on the second frame. That was due to the object being a partial capture. It was on the very edge of the frame in the first image captured, and then it was wholly in the frame on the second image. Our resulting detection time was calculated to be 0.7 seconds. This assumes that there's a uniform distribution of objects entering and exiting and entering the frame, and at 1 frame a second, it assumes on average an object will be in frame for 0.5 seconds before an image is taken of it. So therefore, with 4 single frames and 1 double frame, that comes out to 0.7 seconds. After reviewing all of the detected object images, there were 140 over the 30-minute test. 21 of these, or 15%, had erroneous captures. The objects captured were not people, although they still matched the description of being different than the baseline scene and were hot objects, such as the image on the right, which was a heat fluctuation in the chimney of the apartment complex during the test. Conclusions. In controlled conditions, the system was able to detect people with an acceptable success rate during experimentation. There was a very large cost savings when compared to manned helicopters. Although the detections were at less than 100 feet, which is not your typical aircraft altitude. Given our sensor at 100 feet, your path that you would be sweeping through a search and rescue zone would be only 86 feet. So to improve this, future work would need to improve the range detection, whether it's take a look at infrared-friendly non-glass lenses for optical zooms, or develop system, whether it's fleet flying patterns or what have you, where it reduces the overall system's range to the target to less than 100 feet, so it's acceptable. Additionally, as discussed before, PCB boards, the prototype were to move to this PCB boards, it would reduce weight by eliminating unnecessary components, reduce overall volume. However, the thermal test would probably need to be reperformed as you're changing the enclosure. Look at lenses. GPS sensor fusion was also a hot topic. There was a noted work from CB Chatterjee in which they developed a system to aid aircraft landing using image processing on the camera. So given that they knew the camera's position on the aircraft, its angle relative to the aircraft, and known light patterns on the flight field, it was able to calculate the location of the aircraft. A similar system could be used in reverse, knowing the drone's location and angle of the sensor relative to the object detected in the scene. It could calculate GPS coordinates to said object and report those results over the network rather than just an object was found in a general area. Other operations, such as firefighting, the objects we were detecting were people, so they're relatively small, whereas fire is much larger and also much hotter. The shown images here, although you'd have to look really close, but the image on the left is a visual spectrum camera taking pictures of embers that you can see lightly dotted in the center of the image. The image on the right is is a picture taken from the same position at the same time with an infrared camera, and you can see that it's much more brilliant on the infrared camera. So for wildfires, as they're happening in California, when I was writing this thesis, may still be going on, haven't looked into it. But edge detection and knowing where the wildfire is at any one time may be a beneficial thing to offload to unmanned drones. This sensor flying at a reasonable altitude could be able to outline and do edge detection for these wildfires. And additionally, it could spot smaller fires as embers ride the thermals and generate new fires outside of fire breaks that they typically use for firefighting. Questions?
Will we be flying the drones now?
All the testing that I did for this thesis was static. Afterwards, you guys can come up and feel the box in the enclosure. The box is a fairly small payload that could easily be lifted by commercially available drones today. I estimated in the future works that if this prototype were to be developed into an actual commercial part, a typical drone of approximately $1,500 would be more than capable of lifting this and flying it at ranges.
Would it make sense to use a fixed wing vehicle?
Yes, and fixed wing may be preferred. It depends what type of scenes you're trying to pass. We didn't do any testing at speeds, so that would need to be addressed. But typically fixed wing drones are much more fuel efficient, whether that be combustible fuel or electrical, when compared to your typical VTOL aircraft.
I know you mentioned that if an object or a person is in the water, the visibility for the camera to detect it is low.
Mm-hmm.
Do you think would it be possible, like, for the camera to detect an object much deeper in the water?
That kind of goes back to
Energy exponentially declines as it penetrates through the water. That's why submarines don't have windows.
Yeah, so the image on the right here is actually my hand in like 1 inch of water, and as you can see, the hand is barely visible. Like you can detect a small outline, but the infrared does not travel near, visible light doesn't travel that far in water, and infrared travels even less so. So I don't believe with current technology that infrared would be capable of detecting objects at
So
depth.
out of curiosity, I mean, I know infrared probably won't be able to do that.
Yep.
But do you think getting a different kind of camera would help, like instead of just infrared?
So interestingly, you bring that up. So the product that was used to take the images on the left here in thermal is the FLIR 1 product, which is a cell phone adapter that uses the same sensor. And to get around the low resolution, they actually fused 2 cameras. One was the chip that we used for this system, and one is just a visual spectrum camera. So it actually uses the visual spectrum camera to do edge detection, and then overlays this edge detection on the infrared camera. I believe it was off when these images were taken, but yeah, they have done that, and it works well enough for a commercial product
Yeah.
directly from FLIR.
Makes sense.
Could you tell us about the budget that you used to build this?
So a lot of this budget came from my own pocket for doing the infrared imaging. The camera was the most expensive part. Another reason why I didn't do testing on drones, because drones capable of flying this would be a significant portion of that budget. Additionally, I did get some funding. I don't recall offhand what the grant.
Like you had $1,700.
Yeah.
Were you able to spend the university money on anything?
No, I didn't submit any receipts for that.
Really?
It was a nickeling and dime thing. Didn't feel like trying to reimburse, and I believe they also changed the process. As it was described to me, I had to do all my purchasing through the school rather than get reimbursed with receipts. So
I'm so sorry.
instead of requesting them to purchase something, sending them a link, and then waiting.
Taking you months.
Yeah. So instead of that, I just purchased it offhand. Really wish my company reimbursed me as well, but it's $1,700.
Can't Sikorsky sponsor this so you can actually buy a proper drone and a proper camera?
I think the camera was pretty proper. I
mean,
could.
There's expensive cameras available.
Oh yes. They do not have any process right now to do that. In fact, most of their interns that they have even have to spend their own money when they're working on intern projects for Sikorsky. Yes.
That $1,700 you mentioned, was that through a grant that you received, or was that through the School of Engineering that provided you the money?
No, it was a grant.
It was a grant.
Yeah.
So
I sit on the grant committee, and together we wrote something and we got some money.
Very nice.
But apparently spending it was very difficult. I didn't anticipate how difficult.
yeah, apparently they made some changes recently to that.
I would
It
have
was a
read a
very recent
complaint letter
change,
to
and
Susan
It became very difficult.
France.
Yeah. So the grant process was I had my thesis proposal, and at the time I was still doing the research for which camera was going to be used for this, whether I could use a low-end $25 camera or I needed to go to the $300 camera. So I proposed that I would be purchasing quite a few cameras and doing an evaluation. And I also presented at the Spring Emporium last April, in which I had a poster describing all the differences with the infrared spectrums. Yes.
Will you be relying on the GPS location of the vehicle that's built into the vehicle, or will you have a separate module that is integrated with your system that will track the location of where each image is taken?
So that would be for future work. I've considered it a bit. It would just be how available to the payload software that the GPS would be. If I were to continue this and actually do like fleet operations with a fleet of drones, I would hope that the systems are able to communicate, so I wouldn't need an additional GPS, as you mentioned, and be able to both tell the drone where to go if we needed to do on-the-fly search pattern changes based on sensor inputs, and also reply back GPS data, so we wouldn't have to have an additional module. If that's not possible, yes, I would also include a GPS feature. Additionally, for future work, just to reduce systems further, it may be beneficial to actually integrate this into a printed circuit board that includes drivers for a drone. So both design a drone to fit this system as well. Yes.
Are you trying to me or something?
Sorry. Yes. Just
one more question.
sure.
Did you work on any sort of algorithm to have the drones fly in any sort of pattern, or were you just working on the idea of a drone seeing a person?
I was just working on the concept of the image capturing devices detecting a person. But yes, flight patterns, search patterns, that would all need to be researched, especially now that you have multiple devices that you can send out. Oh, yeah.
What do you envision the price point should be for this drone? Forgetting for the moment that you tried to cut corners and do everything on a budget, because I'm looking at a drone camera here for $7,000, and I'm thinking to myself, if there's $100 million worth of equipment being deployed for search and rescue, people shouldn't care about the cost of small drones.
Yeah, so funny you mentioned that, because while I was finishing up on this, Google sniffing around on my computer, seeing FLIR all over the place and seeing drone all over the place, FLIR actually won a $15 million contract for drones equipped with their FLIR 1 product for the U.S. Army. They are small, single prop helicopters intended to be thrown out by infantry and basically controlled so they can look around corners and
Search
look
and
over.
destroy.
They're actually very small, and I don't think right now they carry any payload to destroy.
Search in order to have the opportunity to destroy.
Yes. Yeah, so those in the military world are very expensive. I think it was $15 million, and they were going to build like a couple thousand or
Have you thought about the
something.
impact of this project if it goes to fruition on Sikorsky's total sales?
So in all the presentations I've seen, specifically for S-92s, search and rescue isn't actually a very large market for Sikorsky. Their commercial market mostly targets transporting oil crews out to rigs and doing research there. So,
Besides, the S-32 may be transporting all the drones out to the region where you're looking.
that too. It's all a battle against time. Additionally, when this was first coming up in the thesis proposal class, my original concept, or my original thought process, is we are starting to have unmanned helicopters. So one of the projects I was actually working on for Sikorsky was converting an old helicopter into an optionally piloted vehicle where the pilot could push a button, step out, and the aircraft could go fly itself. So in those scenarios, if it's equipped with these FLIR turrets, is it possible for the computer to determine these search and rescue operations? And when you have many of them flying around, as you said, need to do fleet pattern control from a higher level rather than just, you search here, you search here. So it's a developing market.
Random stuff.
What's that?
None of the Roomba random vacuuming stuff.
Oh, yeah. Yes.
Does the amount of detail the cameras see, is that impacted by, like, for example, if it's raining outside, like, does the rain kind of like block infrared light? Is that like a significant-
I didn't do any testing in rain. I would assume so, just like it would for a visual camera.
Fog would be a disaster.
What's that?
Fog would be a disaster.
Very possible. So I would have to add that to future testing, in different inclement weather scenarios.
Any other questions? Well, I hope you'll join me in thanking the speaker. Thank you.
And feel free to come up here and actually take a look at the image capturing device I have here.
That's very nice.
hard
So
to
this
beat a
is
little
3D
cat.
printed?
Yes.
And where did you print that?
There was a site available
Oh, you just outsourced it.
out of
Shapeways? Something like that?
yeah, something like that.
Nice.
It'd be hard to beat a watch adapter that sent out a signal for the person in the water.
It's possible, but not everybody falls overboard planning to fall overboard.
Sure, you might be looking for Flight 800 and things that are floating around like bodies.
Bodies don't give off infrared signatures.
Well, they will for
Not
a
for
while.
very long in water.
Yeah.
You have maybe a couple minutes.
No, it was amusing too, using this to capture some images of animals. So one of the tests that I was doing very early on, I was just playing fetch with a dog in the backyard, and the device was just watching me, go back and forth, but there was no dog. Then you get up closer and hold the dog up to the camera, and all the device can see